We're going to talk about a really powerful way to analyze circuits called the node voltage method. And before we start talking about what this method is, we're going to talk about a new term called a node voltage. So far, we already have the idea of an element has a voltage across it, and we refer to that as an element voltage. Or if it's part of a circuit and it's a branch of a circuit, it would be called a branch voltage. And that's a voltage that's associated with a particular element. So now we have the idea of something called a node voltage. And this is still a voltage. It's not anything strange. But if we go over to our circuit here and we label the nodes, let's start labeling the nodes. We'll call this node here, where this junction between this resistor and this source, we'll call this node 1. This is the junction between these two components here. There's another node that's these two resistors connected to this current source, and that's a single distributed node. So we'll call that node 2. And down here, these three components are connected together in a junction, and that's node 3. To define a node voltage, the first idea we need is to define a reference node, the idea of a reference node. Reference node. A good choice for the reference node is usually one that's connected to the terminals of the power sources, or it's a node that's connected to a lot of branches, a lot of elements. And node 3 here is a good choice for a reference node. And the way we mark that is with a symbol that looks like this, a ground symbol. That's called ground in this circuit. There's other kinds of ways to indicate a reference node. That's a common way. You can draw one that looks like the ground, connected to the ground. Sometimes you'll see it with just an upside down T, like that. That's another way to draw ground. So this symbol on a schematic indicates the reference node, and we've picked a reference node to be node 3 down here. So a node voltage is measured between a node and the reference node. In our case, we have this voltage here is the voltage on node 1, the node voltage on node 1, we'll call it V1. And this voltage here is going to be called V2. And in particular, these voltages are measured with respect to node 3. So there's the minus and plus and minus and plus. And we're going to use these node voltages in the node voltage method. So first what I want to do, I want to label my components here. We're going to call this Vs and make it 15 volts. This resistor is going to be R1, and we'll give it a value of 4 k ohms. And we'll call this R2, and we'll give it a value of 2 k ohms. This is the same circuit that we analyzed when we did application of the fundamental laws in another video. Oh, and the last guy here, IS, current source IS, and we'll make that one 3 milliamps. We've analyzed this circuit before. We used Kirchhoff's laws, KVL and KCL, to figure out what the voltages and currents were in this circuit. We're going to do the same analysis, but this time we're going to use what we call the node voltage method. And it's the same application of the fundamental laws. We use Ohm's law, Kirchhoff's laws, but it's in a really clever, organized way that is really efficient. And whoever thought this up was pretty bright, and I'm really glad that they wrote it down and shared it with us. What I want to do first is just write down what are the steps of this method. This method, it's not a theory, it's a method. So it's basically a sequence of steps that you go through to analyze a circuit. And I'll write the list right here. First step is pick a reference node. And we already did that. And the second step is to name the node voltages. And we already did that. We named our nodes V1. That node there is V1, and that node there is V2, with respect to the reference node, which is down there at node 3. Whenever you talk about node voltages, there's always an assumption that one of the nodes is a reference node. Okay, the third step is to solve the easy nodes. And I'll show you what that means in a second. The fourth step is to write KCL, Kirchhoff's current law, equations. And the fifth step is to solve the equations. That's the node voltage method. And we're going to go through the rest of this. We've done the first two steps. And now we're going to solve, what does it mean to solve the easy nodes? The easy nodes are the ones that are connected directly to a source that goes to the reference node. That's an example of an easy node. So V1 is an easy node. So let's solve for V1. V1, I can just, by inspection, I can say V1 is 15 volts. So that's step 3. The other node's not easy. The other node has lots of components and something interesting is going on over here. So this was step 3. Let's label the steps. Here's the step 1. Here's step 2. And here's step 3. Now we're ready to go to step 4, and let me move up a little bit. Step 4 is write the Kirchhoff's current law equations directly from the circuit. And we're going to do this in a special way. But the current law, we're going to perform at this node here, at node 2. We're going to write the current law for this. And that means we got to identify the currents. There's a current. We'll call that a current, and that's a current. Let me give some names to these currents just to be clear. We'll call this one I1 because it goes through R1. We'll call this one here I2 because it goes through R2. And we'll call this one is already IS. Now let's write Kirchhoff's current law just in terms of I, and we'll say all the currents flowing into the node add up to 0. So these two have arrows going out, so they're going to get negative signs when we write Kirchhoff's current law. Let's do that right here. And we write I1 minus I2 minus IS equals to 0. So right now we're working on step 4. And now we're going to do, this is the essence of the node voltage method. This is where we do something new that we haven't done before. We're going to write these currents in terms of the node voltages. So we could write I1. I1 is the current flowing this way through this current. I1 equals V1 minus V2 over R1. That's the current flowing in resistor R1 in terms of node voltages. The current flowing down through I2, now we have to subtract I2, so we just apply Ohm's law directly, which means that the current in I2 is equal to V2 divided by R2. And the last current is IS minus IS. We'll write that in terms of IS like that, and that equals 0. So this means we have now completed step 4. That is KCL written using the terminology of node voltages. And we can check off that we've done step 4.